So in 1934, the man they called the Pope made a leap of faith.
He proclaimed to the scientific world that he'd created elements heavier than uranium. Scientists were electrified and began to investigate Fermi's claim.
In 1938, a team of German scientists, led by chemist Otto Hahn, decided to repeat Fermi's work. Only they quickly found that his claim to have created a new element was wrong.
They identified one of his elements as barium, which has 56 protons in its nucleus, compared with the uranium he'd started with, which has 92. Hahn was intrigued. It's as though uranium had been split in two.
Hahn wrote of his confusion to a colleague, Lisa Meitner, who was working in Sweden at the time. As an Austrian Jew, Meitner had recently fled Nazi Germany and was spending Christmas 1938 at the seaside with her nephew, Otto Frisch.
Meitner puzzled over the mystery, and together with Frisch, she considered the uranium nucleus. Because it's a relative giant, it must be quite unstable. Then they started to think about water droplets, and Meitner imagined the uranium nucleus like a very wobbly, unstable drop, ready to divide with the impact of a single neutron.
Suddenly realized that the uranium nucleus had split in two. Both Fermi and Hahn had witnessed what we now know as nuclear fission. But then Meitner worked through the calculations. She reckoned that the combined mass of the two fragments was slightly less than the mass of the original uranium nucleus, by about a fifth of one proton. She wondered what had happened to this missing mass. Then it slowly dawned on her. Einstein's famous equation, E equals mc squared. The missing mass had been converted into pure energy.
Meitner's flash of insight heralded the creation of the nuclear age, where exciting possibilities for a new form of energy will be countered by its potential for weaponry. This site at Orford Ness used to be a military testing ground, one of the most secret places in Britain. Back in 1939, Lisa Meitner's work on nuclear fission was published as war cast a long shadow across Europe. It shook not just the scientific community. Governments who stood on the brink of conflict became aware of the extraordinary power that could now be wrought from an element. On both sides of the Atlantic, scientists were scrambled to investigate the potential of this new discovery. The result was the US-led Manhattan Project. Its aim was to produce the first atomic bomb. Using scientists from America, Canada, and Europe, the $2 billion project's rapid progress was fueled by fears that Nazi Germany was investigating nuclear weapons of its own.
Both the Germans and the Allies knew that the uranium nucleus could be split by bombarding it with neutrons to release a huge amount of energy. But to be effective, that energy needed to be released almost instantly.
A slow reaction will produce a uranium fire, but no bomb. So both sides poured their efforts into perfecting the key to rapid energy release on a grand scale. A chain reaction. Imagine this ping pong ball is a neutron flying towards an unstable uranium nucleus, a mousetrap. It sets off the mousetrap, which in turn forces a new neutron into the air. Now, in a chain reaction, this is what would happen. One neutron to set it off, but loads of mousetraps of uranium primed and ready. Now imagine each mousetrap of uranium releases a blast of energy, that same energy that Lisa Meitner had calculated. The resulting blast would be enormous. In 1942, Italian physicist Enrico Fermi, now living in America, became the first man to unleash uranium's chain reaction. Uranium. It harbors the power not only to win wars, but to electrify millions of homes. Before its radioactive secrets were revealed, this element's glow under ultraviolet light made uranium glass a desirable asset. About 7 weeks' worth of your year's electricity comes from nuclear fission, part fueled by uranium. And it's used in tank shells as its great weight allows it to drive through armor. But processing uranium for bombs was both difficult and costly.
America would need to come up with a suitable alternative to create its nuclear arsenal.
In California, scientists were focusing on trying to create a new element heavier than uranium.
The key to this was a machine called a cyclotron, which gave rise to this giant machine, a synchrotron. Both machines operate on the same principle. They use huge magnets to steer charged atoms round and round, faster and faster. The magnets are so powerful that if one of them was switched on, it could rip a sledgehammer straight out of my hands. Now, the way to make a new element is to increase the number of protons in a nucleus of an existing element. And in a cyclotron, the way this was done was that when the charged atoms reached 1/10 of the speed of light, they were steered and smashed into a metal target with the potential to create a new element.
Finally, man's dream of creating a building block from beyond the end of the periodic table was about to be realized.
American physicists Edwin Macmillan and Philip Abelson blasted uranium with a beam of particles to create element 93.
They named it Neptunium, the first element heavier than uranium to be created by man. Chemists were once limited to using the elements nature provided. Now, science breached this frontier, creating synthetic elements. And with this new power would come new dilemmas.